So in the last section, we talked about a method to figure out order of reaction in terms of a couple different chemicals, the reactants that are in the chemical. You can also look at a reaction graphically, and we may be able to determine the order of reaction by interpreting a graph. And then once we know the order of reaction, we have a couple equations that are available to us that are derived, by the way, from calculus that you can use to obtain, maybe solve for a concentration at a period of time. You could figure out how much time does it take to get to a certain concentration, and I guess you could also solve for the rate law constant. So we're going to talk about three different types of orders of reaction in this section here. We're going to talk about zero order reactions. They're going to be the simplest of the three, so we're going to spend the least amount of time talking about them. First order reactions, and we're going to spend the most time talking about them because the majority, not all, but the majority of the reactions, I shouldn't say the majority, more reactions are going to be that fit that profile. And then also we're going to talk about second order reactions. So if you had a first order reaction, the generic rate law would look like this. And we don't typically put the one in there, but I'll put the one in there. So this one deals with a reactant to the first order. And important to note that if you would double, let me erase that one there. If you would double the amount of A, you would double the rate, okay? Because it's a power of 1 there. We have a couple equations that we can use, and this, I believe, is in your equation sheet, so you don't have to memorize this. And this uses the natural log. So the natural log of a concentration at a period of time minus the natural log of the concentration initially, that's what that little O means there, equals negative K, the equilibrium constant, the rate law constant, times time. Okay, so we can solve for any of those parts. Often we'll have a graph, and over here will be natural log of A on the y-axis, and then time will be on the x-axis. And if we plot a series of concentrations over time, natural log of those, you will get, that's not a very straight line, but when we take the best fit of that, that slope will be related to K, in this case, a negative K. So if we were able to graph it, we can figure out K. We've already learned one other method to solve K, and now I guess we have a third method to solve K if it's a first order. So we're going to do a series of questions that deal with that, and I've already provided the answers. I'll put the work up here to go with that. So we have a reaction of cyclopropane to propene, and it's already been determined that it's first order. It's already been determined what the rate constant is. So probably, most likely, is that someone graphed that natural log of the reactant versus time, the cyclopropane, and found that they have a straight line that would indicate first order. So then they took that slope of that line, negative slope of that line, and that's the K value. Okay, so this question says, hey, we start off with 0.25. What would be the concentration after 8.8 minutes? Now, we can't use 8.8 minutes in the question because the rate law constant is in terms of seconds. So I've already done that conversion for you guys. So now it's plug and chug. It's a little more in-depth plug and chug, but it's plug and chug. So we don't know the concentration A at a certain point in time, but we know the concentration initially, and then that's going to equal the rate law constant. and the time. And I left my units out here, but just to save a little bit of room. But remember that again, those units that are in the rate law constant have to match up with the time. So if you have a graphing calculator, you might be able to do this all in one long problem. If you have a scientific calculator, you might have to break this up into little steps. But natural log of A, we don't know what that is. Natural log of 0.25. There's a lot of digits on here, but just to save a little space, I'm only going to write a few of these, but on my calculator, I'm leaving all of them in there. And then I multiplied those two terms on the right here together. Whoops. Okay, so you get the negative 1.386. Get that over on the right side, and then you're going to have to divide both sides by natural log. And to do that, you're going to have to use wherever your natural log key is. The second key of that is going to be an e to the x key. We can call that the anti-natural log, but you're going to have to use that button. And when you finish up that math, you will get, now you'll get more digits than this. Actually, probably we should have went to 2 sig figs because our measurements were 2 sig figs. So let's actually amend this answer here to 2 sig figs. Okay. So that time we solved for a concentration. This time, the next question, how long, we're going to solve for time this time. So very similar, same equation, but we have a couple molarities already. So our molarity at a point in time was 0.15. Our initial molarity was 0.25. Same constant, because it's the same reaction and the same temperature that reaction takes place, but we don't know time this time. So when we solve for time, we're going to get 762 seconds. So take the natural log of 0.15, take the natural log of 0.25, subtract those two values, divide by negative 6.7 times 10 to the negative fourth, and you'll be left with 762. Let's make sure that we like that number. So in the previous question, it took 528 seconds to go down to 0.18. So if we want to go a little bit lower than 0.18, it's going to have to take more time, and that certainly is more time than the last one. So that appears to be in the ballpark of correct. You guys should try to be analyzing these if you can each time. How long will it take to convert 74%? Well, now we don't have a molarity. That's okay. So let's talk about what that means. So if we started off with 100%, if we convert 74%, how much do we have left? We have 26% left. So I'm going to put start, and it's not really a finish, but at this point in time, it's 26% left over. So we can do the same question that we just did before, but with new numbers. So 26% is 0.26. Natural log of the starting material, 100%. Can use 1. Equals the same rate law constant that we've been using, and then we don't know time. So it's almost identical question as the one previous, except this time we have different numbers. And so when you solve for t, this time it's 2010 seconds. Okay, and if you look at these two answers, we probably should have amended these also to 2 sig figs. If you're off by 1 sig figs on the test, you're going to be fine and under almost all circumstances here. This one's going to be very tricky to get into 2 sig figs. We'd have to do a scientific notation on this one. So we'd go 1, 2, 3 spots, and that would get us into 2 sig figs. Okay, so another first order reaction. This is decomposition of ozone, and someone measured this concentration of the reactant over time. And so the question is, are these values consistent with first order? If so, determine the rate constant. With your graphing calculator, what I would do, you could do this old school, get a piece of graph paper out and have a X and Y axis, natural log of ozone. We'll just call it A because I don't have a lot of room right there. And then time. And I would plot the natural logs of all those concentrations versus time. And if you got a straight line, then that's consistent with first order. And then you just have to look at that slope. The negative slope would be the K value. So I think we did that. And actually, again with your graphing calculator, or you could use a graphing program, or you could do that old school and do rise over run, and we would get a slope here. And that slope is related to the K value. The negative slope would be the K value. And so there we go, first order. If it wouldn't have been a straight line, it's not first order. We don't know what order it is, but we know it's not first order. Okay, next item. We're going to introduce another vocab here, half-life. And the typical unit to designate half-life is a half T, a subscript there. You could use T and that'd be fine, but typically people use that 1/2. And for, again, using some calculus, someone else derived an equation to solve for half-life for first order reactions. This is only going to work with first order reactions. So natural log of 2. And so some people actually just write this as 0.693. If you do the natural log of 2, I'll do it right now on my calculator. It gives you a bunch of digits after the 0.693. But for all intents and purposes, that would be fine, 0.693, divided by our rate law constant. So here's another way that you could actually solve for rate law constant. Okay, so again, this only works for first order. And you know what, this is a good time to mention this, that anything, any nuclear decay, any isotopes that are decaying, those are all first order reactions. Okay, just in case that comes up at some point, carbon-14 is a isotope of carbon. It decays by first order. They all do. Okay, so what do we got here? Decomposition of ethane to methyl radicals, first order. So someone has already determined that. The rate law constant is given. Calculate half-life. So T1/2 equals natural log of 2. We could write that, or we could write 0.693 divided by 5.36. Whoops, not 1. And do that math. And what do we get there? 1290 seconds. So that's the half-life. What does that mean? That means if you started off with 100% of your material, for you to go down to 50% of your material, it would take 1,290 seconds. You could continue doing that. It'll approach zero, it will never get to 0%. So then 50% to 25% would take another 1,290 seconds, and so forth and so forth and so forth and so forth. Typically, we will have questions that you have to use both of these equations. And how do you know you'd have to use both these equations? Let's figure it out. So it gives you a half-life. It says calculate rate constant for this reaction and determine the amount of time needed to be 75% complete. So I'm going to show you a hard way first and then an easy way second. So the reason we're going to do the hard way is because it actually asks to solve for rate constant here. So T1/2 is 20 minutes, and that equals 0.693 divided by K. So K in this case is going to be 0.0346. It's not very good. 4. And I am not rounding this because I'm not ultimately done with the question until I figure that out. So there's probably more digits after that 5, but this will at least give us enough that it's not going to impact our answer by rounding there. Now that we have a K value, we could solve, by the way, this is called the integrated rate law, the one that deals with the natural log of A at a certain point in time minus natural log of A initially equals negative K times time. So that's the integrated rate law. So we can kind of now plug some numbers in and solve. So 75% complete means that we have 25% left over. And remember, we started with 100%. We have our rate law constant. I don't have a lot of room over here, but let's see if I can get this in here. And then we're solving for time. So rearrange our equation, move everything so we can solve for time, and we're going to get something in the range of 40 minutes. We could have done this a lot easier. So how could we have done it easier? Well, we start with 100%, remember? And then over one half-life, we'll be down to 50%. Well, how long does that take? Each half-life has already been told to us it's going to take 20 minutes. And then if we want to go down to 25%, it's going to take another 20 minutes. 20 plus 20 is 40 minutes. I think that's going to be a lot quicker. If you can do it quicker, try to do it quicker. Could you use the integrated rate law like I demonstrated? Absolutely. But I think it's easy to tell. It'd be a lot easier to screw that up with your calculator, punch in the wrong digits, forget a sign somewhere along the line. So it could be a lot easier just to do the method I used on the left there. So now let's quickly visit 0 and second order. And they have their own unique derived mathematical equations. The second order uses, instead of natural log, 1 over concentrations. Very similar though. If you would graph 1 divided by concentration versus time, you would get a straight line if it's second order. Now this one goes through the origin, so actually the K value and the slope are going to be identical terms. Because there is a 2 there, second order, and then also what this means is if you would double the amount of A, you don't double rate, you would quadruple the rate. Okay, and there is also a unique half-life equation, and the integrated rate law for second order is in your equation sheet. I don't think the half-life equation's in your equation sheet. So the math would be identical. You just have to know to use second order equations where appropriate if it says it's second order, or if you have a graph that you can interpret as second order. And then we could do the same thing with zero order. And that graph would be just concentration versus time, and you would get a straight line. Yeah, that doesn't look too straight there, but take my word for it, that's straight. If you get that, then it's zero order. And we could actually put the A in here, but it would be to the power of 0. So if you take anything to the power of 0, that's 1. So that's why people typically don't put the A in there. So rate equals the rate law constant. This one's definitely the most simplified. So that would mean least likely to be on our test or on the AP exam. But it does have its own unique integrated rate law. This one doesn't use 1 over concentrations. It doesn't use natural logs. It just uses concentrations. And we could, by the way, rearrange this so it would look like the other ones. So maybe that might be more comfortable for you there. Okay. And then we have also a half-life. By the way, zero order, we're not going to get many of those examples, but if you would change the concentration of the reactant, it has no impact on the rate. This certainly is not a reaction, but if you had an hourglass here and it had sand up here, it doesn't matter how much sand you have, the sand can only come out at a specified rate. If you have a little bit of sand, it comes out of the same rate as if you had a lot of sand. So that's about my only example I'm going to have for you that's real world for zero order. It doesn't come up too often. And lastly, let's try to interpret some graphs. I would say this would be a very typical question. Actually, I guess there's two questions. So we have graph set 1 and graph set 2. And we have to be able to look at these and interpret what kind of order of reaction. All we're looking for is the straight lines. So this straight line appears with concentration over time, so that is zero order. And then this graph set 2, the straight line is with natural log, so that is first order. By the way, if you didn't get a straight line with any of these, then either graphically something went wrong, experimentally something went wrong, or it just isn't zero, first, or second order. Are there other orders of reaction out there? There are. Are there ones we're going to talk about in this class? No. And I think that concludes. Yep, that is done with zero, first, and second order rate laws.